All right, so I'm Charles Bailey. I'm responsible for high power GaN. High power meaning above about 800 watts, or let's call it above 1 kilowatt. This is mostly into data center rack power supply segment, industrial and solar, and then EV focused on the onboard charger and the DC to DC converter, not so much the traction inverter. Those three segments, you'll see demos of it in a bit, where we have integrated GaNSafe into those components along with 650 volt SiC. We'll talk about the hybrid power supply concept, which is very important, taking advantage of the best behaviors of each technology. All right, so you heard from Gene and Dan earlier a lot about the genesis of Navitas, how it all got started, and the very accurate assessment that GaN needed an integrated gate drive. And that's what Navitas started since it was founded. I was actually competing against Navitas in the early days of GaN. I was at a discrete GaN company, and this was pointed out to me by customers as, this is the future of GaN. So you've also heard from Tom just preceding me that all of this has been in lower power segments, adapters and mobile. And that was also a very good business decision because this is fast time to market, it's high volume, and that's where Navitas got the reliability and the cost. The reliability up, this architecture was proven, right? And of course the wafer cost came down, as with all semiconductors, dependent on volume. So then after 2017, the idea of moving that architecture into higher power came around, and then I joined in 2020. And by this time, it was very clear to customers, to other semiconductor companies, partners, right? The right way to design with GaN is with integrated gate. And as you move up in power, this becomes more and more apparent. And why? It's Ohm's law in the frequency domain. Delta V equals L di dt, where L is the gate loop inductance. Di dt is, of course, the switching current, which goes up as you move into higher and higher power. So I asked the question rhetorically, where is GaN in high power, right? There's been a lot of discussion about it. As Gene said previously, we are here to do that, okay? So what we did is straightforward, I think, as you'll see. We took the GaN Fast and the GaN Sense architectures, all of the benefit of that analog IC design with GaN, and we took it to the 4th generation and made GaNSafe. So what is in GaNSafe? The protection feature really that was added, in addition to the ones that you've already seen, the most important one is, in addition to ESD protection, of course, is short circuit protection. And why is this important? Because GaN it's a more perfect switch, right? It switches much faster, and it also conducts very well, even under short circuit conditions. So the short circuit withstand time is less than SiC or IGBT. So you need a very fast acting, low latency protection, and that's what we integrated on chip with SCP. All right, so what is great about GaN? It's got obviously very low gate charge, very low output charge. And this is what makes it ultra low switching loss. But it has a low threshold voltage, okay? And together with LDIDT, you can easily get into a situation of cross-conduction or ringing on the gate, right? Hence, the need for integrated gate drive, which we put into GaNSense. Next, reliability on the gate. GaN has a sweet spot around 6.7 volts VGS, gate to source voltage. And that's where the saturation of the GaN FET is optimized. Meanwhile, you can push VGS above 7.0 volts, but the lifetime reliability can be impacted. And of course, with data center, industrial, solar, and automotive, we're going for 25-year plus lifetimes. So the reliability limit on the gate also is a concern. Again, this is why integrated gate drive, precision voltage regulation, so critical, especially in high power. And then finally, there's no negative gate drive required. This is a crutch used by discrete GaN, right, to try to prevent cross-conduction at high power. But what does that do? It affects the efficiency, right, in each third quadrant operation. So we don't need that negative gate drive, as you'll see. Okay, so lastly, I'm jumping ahead a little bit. GaN has to go, as all power transistors, especially in higher power, into a robust, industry standard, high reliability, thermally optimized, and mechanically robust package, right? So the GaN that you've seen, a lot of it, most of it is not in that robust, thermally optimized package. There's GaN packs, which has got a very thin thermal pad, we'll see in a second. And then the QFN, also from a leading IDM, not so thermally robust or mechanically. So GaNSafe starts in the toll package. We will introduce other packages later. But on the left side, we're comparing a 45 milliohm max, and I will only speak about maximum RDS on, not typicals, right? 25 degree C max. So on the right side, GaNSafe, 45 milliohm max. On the left side, a leading IDM of power semiconductors with a discrete GaN device, right? No integration, put into a toll package. By the way, these are PCBA footprint compatible. So what happens to the discrete GaN device? You can already start to see, hopefully, from the lighting, you're already getting a lot of ringing. And this is at, a 30 amp load step, slowing down the discrete gate a bit, right? With, of course, a 400 volt. All of this is targeted at 400 volt DC bus, right? So you're already starting to see this ringing. And the ringing comes from the inductance of the package. So with GaNSafe, the inductance of the package is no problem. That's overcome because we have integrated gate drive, okay? What power level does a 42 milliohm max power transistor get to, say, the LLC single or non-interleaved in a 1.6 kilowatt rack power supply? If it's interleaved, 3.2 kilowatts. You get the idea. So kind of in the sub 3 kilowatt range. Now, if you want to go to OPCs, 22 kilowatts, you have to get down to 25 milliohm max RDS on. And what happens? So there is no, until GaNSafe, right? GaNSafe will be the first 25 milliohm part max in a robust package with integrated gate drive. What happens when you try to do that in a robust package with inductance? Keep in mind, GaN Systems has a 25 milliohm are actually a 32 milliohm max part in the GaN packs package, not thermally robust. I'll show you that in a minute, okay? And why the GaN packs package? Super low inductance. And they knew they had to do that because they didn't have integrated gate drive, okay? So if you did put discrete GaN all the way down to 25 milliohm max for a 22 kilowatt OBC LLC section, it's a formula for cross conduction, all right? You either violate the SOA of the part or you blow up the power stage. All right, so we went through electricals, right? Now we go to thermals, equally important. What is heat? Heat is a scalar quantity. It's not a vector. So how does it move? With area. It's spherical spreading. Power packages must, they can't inhibit that spherical spreading, and they have to help it, okay? How do you do that? Thicker lead frames, power pads. This starts the process of spherical spreading, which is then continued into the system thermal design, okay? And that is how you get, the power package has to work in conjunction with the system thermal design. And in power electronics, the thermal design, more and more important because of higher power density, right? So, all right, so the GaN packs package, a whopping 47 micron thickness, right? On the other side, toll, 10 times thicker, 500 micron thick lead frame. In the middle is the QFN used by well-known GaN IDM, 200 microns thickness. You're not going to get any thicker lead frame on a QFN because of the aspect ratio of the pins, right? With that many pins, you can't, create skyscrapers. There is a XY for the pin dimension, and that limits the thickness of the thermal pad for the QFN package. Toll does not have that limitation. So then, on the right side, what happens? So these two flow therm simulations are apple to apple, identical. In this case, it's convection, airflow. And power dissipation, the system thermal design, everything is identical. And the same power put into the device. The only difference is QFN versus toll. You already see a 12% lower junction temperature. Why? Heat spreading is way more effective, okay? So we've walked through, let me summarize. GaN is great. It's got ultra low switching loss. It is a near perfect power switch, but it has limitations, a low threshold voltage. It will suffer from LDIDT gate ringing if you don't have gate regulation integrated. It has very short circuit withstand time. You add SCP at the chip level. And as all power transistors in high power, you got to have a robust power package. And that's what we did with GaNSafe. So now, how does it work? Okay, so this is a public example, right? Spin-off of a huge telecom company in China. Alpha Fusion produced this unit publicly, claiming it's a 3.2 kilowatt CRPS, which it's not, okay? Versus the unit that you will see in a bit, right? We designed in our system design center a true 3.2 kilowatt CRPS It's true 3.2 kilowatt over the voltage input range, over the titanium efficiency range, titanium plus, right? It's not sufficient for a power supply designed just to meet titanium because you'll have fallout in manufacturing. There's a CPK, right? So you have to go above that to make sure that in high volume, the power supply is always titanium. And yeah, hold up time, very important for data centers, right? Critical for power outages and the power density. We have a true 100 watt per cubic inch system designed, in this case with GaNSafe. We'll also show you a 4.5 kilowatt CRPS in the same form factor using SiC in the PFC. My colleague will be up in a minute to talk about SiC. What are its benefits? Super low, in the case of GeneSiC, RDS on Tempco, right? And very high thing called saturation current makes it great for hard switching topologies in high power. So like the input stage PFC for an onboard charger is an example. But here, the whole design is GaNSafe. So at the bottom line, it took 12 pieces of 32 milliohm GaN packs to have a system that didn't work as well as a system with 8 pieces of lower RDS-on GaNSafe. There it is, okay? No negative gate drive, no loss of efficiency there, way better package thermally. This, and you ask the question, like, where is GaN in high power? These are the reasons why, okay? So when Gene and Dan stood up and said, we're here to bring GaN into high power, this is what we're all moving towards, okay? So the industry, recently, this has been introduced to the industry, and they get it, right? We had a GaNSafe launch in Taipei attended by 6 out of, the usual suspects of ODMs, and then another 3 OEMs, all senior directors or VPs of their respective divisions. They got it immediately because they've been working, their teams have been working with discrete GaN in compromised packages for years. And so GaNSafe is truly a beacon for GaN in high power. Please, if you have any questions, don't hesitate to stop me. Okay, how do we do this? I'm not going to go through this in gory detail, but it takes one thing that is a technical competency of Navitas. Gene and Dan touched on it, but it's, or maybe they didn't, ultra-low quiescent analog IC design, okay? That's a craft all in itself. And so you have to design this power IC not to use so much current to power itself, right? So that's starting point. And then second big thing, the number of pins or the terminals, the number of I/O, right? And if you look at this, there's only 4 terminals. Drain and source are on every power semiconductor, gotta be, right? It's how the power is converted. Source Kelvin, normal also 3rd pin. So 3 out of the 4 pins are on virtually every power transistor. The 4th pin would be the gate if it were a discrete power transistor, but it's not. We call it V drive. So through this one I/O, one pin, a very clever power IC. Actually, Dan was the initial thought behind this. So from the V-drive pin, we have an internal 5-volt supply, which supplies everything else for logic, and then level shift, PWM deglitch, which is in, got to be there in every driver, and UVLO, right? Got to have that. So that block is powered, and then the voltage regulation. And one of the things that we added in GaNSafe is a better PTAT, proportional to absolute temperature, a flatter VGS regulation over temperature, minus 40 to plus 150, okay? And then what else? Short circuit protection, again, this is true DSAT detection, right? It's not a glorified OCP, right? That's a different behavior. You want to detect when the drain is going into saturation. That's the clue of short circuit, right? It's not a overcurrent. And by the way, Tom talked about analog controllers for mobile and consumer. That's true. And they don't have sophisticated functions in many cases, like OCP and OTP, over temperature, over current. We integrated that. In enterprise, industrial, solar, et cetera, and automotive, DSPs and microcontrollers are used. And so overcurrent and over temperature already there, but what they don't have is short circuit protection super fast, and you need to have that. By the way, our SCP is 350 nanosecond latency from initiation of the event to shutdown. Super fast and accurate. And you'll also see a demonstration of the short circuit protection feature. So we've got that. And then Miller clamp, finally, there's actually 3 pull downs. The Miller clamp acts every switching cycle, right, to prevent the gate from turning on when you don't want it. There's a soft pull down that works with short circuit protection. You want a soft pull down from SCP because otherwise you'll have an overshoot on the drain, okay, and you don't want that. And finally, there is a device that will keep the gate off even before the UVLO is active. So as soon as there's voltage on the drain during power on, the gate is off, held off, which is what you want. So it's a safety feature. This is how we do GaNSafe. Questions? Okay, when I went through this in Taipei with all of the computing data center rack power supply guys, they got it. All right, you've seen kind of this before, but it's a refresher. GaN, as Tom said, it's great in higher switching frequency because of the ultra low switching loss. And that gets you smaller magnetics, smaller passives. And in this case, this comparison is versus CoolMOS from a world-leading high-performance 650-volt silicon MOSFET supplier. So you get, not only do you get higher switching frequency at higher efficiency, hence you get a savings, a smaller size, and a higher power density, you also get a BOM cost savings, okay? And this is another business point, okay, for Navitas. So, GaN suppliers have been talking about this threshold of, when GaN component cost crosses the CoolMOS threshold, right? We've been hearing this for 8 years. I'm happy to say Navitas is a very aggressive and technically competent company everything we do is actionable, right? Very specific plans regarding GaN process development, capacity, and cost. But at the system level today, there is already a benefit to using GaN, and that, of course, is because of the savings in the passives and the magnetics. Okay. All right. So we've introduced the first 4 part numbers out of a 9 part number sequence eventually. It's available. It's already been sampled to about 40 beta customers in most, to start, a lot in rack power supplies, but also solar microinverters and PV string inverters and onboard chargers, all of the usual beta customers that you'd imagine in those 3 segments. And I'm talking about these 3 segments, but keep this in mind. We are already saving system BOM cost in these 3, and you'll be able to see that. So that's great. And then we will cross this, silicon MOSFET threshold of component cost. And when that happens, it's an avalanche, right? Then it's $6.6 billion additional TAM above mobile and consumer. There's no reason not to use GaN, right? One other thing. Once suppliers design with high switching frequency, they can never go back, right? You can't make it bigger. You can't make it less efficient. You always have to go forward. So wide band gap, SiC and GaN, it's a turning point for the entire power electronics industry, and the world will never go back. Okay. My SiC colleague will come up in a minute. Any questions, please feel free. All right.